Look at the walls around you. You likely perceive them as solid boundaries, markers of a fixed location in a predictable three-dimensional grid. You trust your senses to report the presence of matter and the passage of time as objective, universal constants. This trust is the foundation of your sanity. However, modern cosmology and observational physics have begun to document a series of measurements that suggest this stability is a localized illusion. We have looked into the deep field of the universe and found structures that violate the fundamental principle of uniformity. We have measured the vacuum and found it possesses a tension that contradicts our understanding of atomic stability. The data does not suggest that our theories are slightly off. It suggests that the reality you inhabit is a narrow, atypical slice of a much more hostile and illogical totality. These are not thought experiments. They are the mathematical and observational residues of the universe as it actually is. We are forced to confront a central conflict. Why does the universe appear to follow laws that, when followed to their logical conclusion, render our existence impossible? The great attractor and the illusion of stillness. You feel as though you are stationary, but you are currently being pulled toward a point in space that remains hidden behind the opaque dust of our own galactic plane. As you sit in your chair, you are participating in a multi-layered kinetic journey that defies your vestibular system. The Earth rotates on its axis at 1,600 kilometers per hour. It orbits the Sun at 107,000 kilometers per hour. The solar system, in turn, is being swept around the center of the Milky Way at speeds exceeding 800,000 kilometers per hour. Yet even this orbital motion is not the final vector. When we subtract these local movements and look at the largest possible frame of reference, the cosmic microwave background radiation, we find that our entire galaxy, along with everything in our local neighborhood, is screaming toward a specific coordinate in the direction of the Centaurus and Hydra constellations at roughly 600 kilometers per second. This motion is not random. It is a systematic, coherent drift. We are being hauled across the void by a gravitational influence so massive that it warps the expansion of the universe itself. Astronomers call this the Great Attractor. The difficulty in understanding this force lies in its location. It sits directly behind the zone of avoidance, a region of the sky where the thick, luminous disk of the Milky Way acts as a physical barrier to our telescopes. The gas and dust of our own home galaxy absorb and scatter visible light, effectively blinding us to the very thing that is determining our long-term trajectory. For decades, we could only infer its presence by the way other galaxies were behaving. We observed thousands of galaxies across millions of light years, all appearing to flow like water down a drain toward an unseen center of mass. When we use X-ray and infrared astronomy to peer through the galactic dust, the reality becomes more unsettling. The Great Attractor is not a single object, but a localized concentration of mass equivalent to tens of thousands of Milky Ways. It is the heart of the Laniakea supercluster, a massive web of 100,000 galaxies spanning 520 million light-years. We are part of this web, a single thread being pulled toward the center of a gravitational well that we are only beginning to map. However, the paradox deepens when we measure the speed of our approach. Even the immense mass of the Great Attractor is not enough to account for the velocity at which we are moving. The math does not add up. The flow is too strong. This suggests that the Great Attractor itself, along with our entire supercluster, is being pulled towards something even larger and more distant. The Shapley supercluster. This realization dismantles the notion of cosmic equilibrium. We have long assumed that on a large enough scale, the universe is homogeneous, a smooth, uniform distribution of matter where no direction is special. But the existence of these attractors suggests a universe defined by massive, lopsided imbalances. We are not drifting in a calm sea. We are caught in a cosmic current, falling through a landscape of invisible pits and peaks that were decided in the first micro-instance of the Big Bang. The implication is that your sense of here is entirely provisional. You are a passenger on a structure that is losing its battle against an unseen gravitational master. You are currently 250 million light-years away from the center of this anomaly, falling at a rate that defies human comprehension, toward a destination that remains perpetually obscured by the very stars you call home. The fine-tuning of the vacuum catastrophe. There is a specific value for the energy density of empty space, and if you were to change it by a fraction so small it defies human notation, the universe would have either recoiled into a point or expanded too fast for an atom to ever form. We often conceptualize nothing as a total absence, a void where matter and energy are simply removed. But in the language of modern physics, the vacuum is not empty. It is a field, possessing a fundamental tension known as dark energy or the cosmological constant. This energy exerts a repulsive pressure, pushing the fabric of space-time outward. The measurement of this pressure is the most precise and most terrifying calibration in the known cosmos. If you were to increase the strength of this vacuum energy by only 1 part in 10,120, the repulsive force would have become so dominant in the early universe that matter could never have coalesced. Before the first hydrogen atoms could find one another, before gravity could draw gas into the crucibles of stars, the vacuum would have shredded the young cosmos. Space would have expanded so violently that every particle would be isolated in an infinite, lonely void, forever beyond the reach of any other particle. There would be no chemistry, no light, and no witnesses. Conversely, had the value been slightly lower or negative, the universe would have acted like a spring stretched too far. Almost immediately after the Big Bang, the inward pull of gravity and the negative pressure of the vacuum would have caused the universe to collapse back upon itself. The entire history of time would have been a brief, frantic flicker, ending in a big crunch, returning all of existence to a singular point before a single heartbeat could have occurred. The discrepancy between what our theories predict and what we actually observe is what scientists call the vacuum catastrophe. When we use the tools of quantum field theory to calculate how much energy should be contained within empty space, the math provides a number that is 10,120 times larger than the amount we measure through telescopes. To put this in perspective, this is the largest mismatch between theory and observation in all of science. It is not a small error. It is a fundamental breakdown of our ability to describe reality. If the calculated energy of the vacuum were real, the universe would have exploded into oblivion a trillionth of a second after its birth. The fact that we are here to measure it means that something, some unknown mechanism or staggering coincidence, has canceled out the energy of the vacuum with a precision that defies logic. It is as if you threw a handful of sand into the air, and every grain landed perfectly on its edge, balanced against a hurricane. This suggests that the stability of your world is predicated on a cancellation of forces so perfect it feels artificial. We are forced to ask why the vacuum is so quiet when it should be screaming with energy. If this value were even slightly different, the atoms in your body would not just fall apart, they would never have been permitted to exist in the first place. You are the beneficiary of a cosmic clerical error, living in a narrow sliver of stability that the rest of physics says should be impossible. The universe does not care about your survival, yet it appears to be suspended on a razor's edge of mathematical tuning that allows you to breathe. We find ourselves in a reality that is statistically absurd, and we have no explanation for why the vacuum decided to be so hospitable to the matter that makes us. The Boltzmann brain and the probability of memory. Statistically, it is more likely for a single conscious entity to fluctuate into existence out of the void with a full set of false memories than it is for an entire universe to evolve over billions of years. This assertion is not a fragment of Gothic horror, but a rigorous consequence of the second law of thermodynamics. To understand this, you must first accept that the universe prefers disorder. Order is expensive. It requires an incredibly specific, low-entropy starting point, like the Big Bang. Over billions of years, that order decays, scattering energy and matter until the cosmos reaches a state of high-entropy equilibrium, a lukewarm, featureless soup where nothing happens. In such a state of equilibrium, which the universe will occupy for an eternity, random fluctuations become the only source of events. Given enough time, vast, unthinkable eons, particles will occasionally bump into each other by pure chance and form structures. This is the logic of the infinite monkeys theorem applied to the vacuum of space. Most of these fluctuations will result in nothing more than a momentary clump of atoms or a brief spark of heat. However, the probability of a fluctuation occurring is inversely proportional to the amount of order it creates. It takes an enormous, statistically impossible fluke to create a universe with 100 billion galaxies, all precisely tuned to produce stars, planets, and biological evolution. It takes far less luck to fluctuate a single, isolated human brain into existence for one fleeting second. This hypothetical entity, known as a Boltzmann brain, would appear in the void already wired with synaptic connections. It would possess the firing neurons that represent the memory of a first kiss, the smell of rain, and the specific sensation of reading this exact sentence. From the perspective of that brain, its reality is indistinguishable from yours. It perceives a room, a body, and a history. But it is an illusion, a momentary statistical glitch in a dying universe. Because the universe will exist in a high-entropy state for infinitely longer than it will exist in its current, organized state, the number of Boltzmann brains produced over the total lifespan of the cosmos should vastly outnumber the number of real biological brains produced by evolution. This leads to a terrifying conclusion regarding your own identity. If you are a conscious observer, and you know that the vast majority of conscious observers in the history of the universe are fleeting fluctuations in the void, then it is mathematically probable that you are one of them. The data you rely on to prove you are on Earth, your childhood photos, the scars on your skin, the historical records of the 21st century, are merely the internal architecture of a brain that flared into existence a moment ago and will dissolve back into the vacuum in the next. We have no way to disprove this through observation, because any observation you make is processed by the very brain whose origins are in question. We are left with a paradox that threatens the foundation of science itself. If we trust our theories, they tell us we are likely an accident of entropy rather than a product of history. If we are an accident of entropy, then our memories of those very theories are unreliable. The universe, in its pursuit of absolute disorder, has created a scenario where the observer can no longer distinguish between a lifetime of experience and a single dying spark of thought in the dark. The cosmological principle and the giant arc astronomy relies on the assumption that the universe is homogeneous on a large scale. Yet we have observed a structure 3.3 billion light-years long that mathematically should not exist. This foundational assumption is known as the cosmological principle. It dictates that when you view the universe at a sufficiently large scale, beyond the local clusters of galaxies, the distribution of matter should be smooth and uniform. To an observer anywhere in space, the cosmos should look roughly the same in every direction. This is not merely a philosophical preference for symmetry. It is the mathematical bedrock upon which our understanding of the Big Bang and the expansion of the universe is built. If the universe were not homogeneous, our equations for gravity and light would only apply to our local bubble, rendering the rest of the cosmos a lawless frontier. For decades, the threshold of homogeneity was thought to be around 1.2 billion light-years. The logic was simple. While galaxies clump into clusters and clusters into superclusters, the sheer age of the universe has not provided enough time for gravity to pull matter into structures larger than this limit. Gravity moves at the speed of light, and the universe is only 13.8 billion years old. There is a physical speed limit to how far an atom can travel to join a larger collective. However, in 2021, researchers discovered the giant arc. Spanning 3.3 billion light-years in the constellation of Bootes, this crescent-shaped string of galaxies and gas clouds is 3 times larger than the theoretical limit. It represents a massive concentration of matter that should have remained dispersed. To find the giant arc is like walking across a desert of uniform sand and suddenly encountering a wall of rock 1,000 miles long. It does not belong there. It violates the statistical expectations of a random, expanding system. The giant arc is not an isolated anomaly. It sits near another gargantuan structure called the Big Ring, which is 1.3 billion light-years in diameter. Together, these structures suggest that the universe is not the smooth, isotropic soup we assumed it to be. Instead, it appears to be organized into massive, coherent patterns that defy the known timeline of cosmic evolution. If gravity has not had enough time to build something this large, then these structures must have been seeded during the first fraction of a second of the Big Bang. Or they are the result of physics we have yet to identify. The implications of this measurement are quietly devastating for modern cosmology. If the cosmological principle is false, then our standard model of the universe is an oversimplification. We use the uniformity of the sky to calculate the age of the stars, the rate of expansion, and the nature of dark energy. If the universe is actually lumpy and structured on scales we cannot explain, then our measurements of distance and time across the deep field may be fundamentally distorted. We are forced to confront the possibility that we are living in a universe that possesses a preferred direction or a hidden architecture. The giant arc suggests that the void is not a blank canvas, but a territory marked by gargantuan scars of matter that should not exist. We are looking at a structure so vast that it forces us to reconsider whether the laws of physics are truly universal, or if we are merely observing a small, deceptive patch of a much more complex and irregular whole. The black hole information paradox. If you were to fall into a black hole, the laws of physics dictate that the information making up your identity must be preserved. Yet, general relativity ensures that every trace of you is deleted from the observable timeline. This conflict is not merely a technical disagreement between two branches of math. It is a fundamental crisis regarding the nature of history itself. In the framework of quantum mechanics, information refers to the specific quantum state of every particle, the data that distinguishes one atom from another. This information is considered indestructible. If you could track every atom and every energy state, you could, in theory, reconstruct the past with absolute certainty. This is the law of unitarity, and without it, the predictability of science collapses. However, a black hole presents a physical boundary that appears to violate this law. According to Einstein's general relativity, once you cross the event horizon, all paths lead inevitably to the singularity, a point of infinite density where the known laws of physics cease to function. From the perspective of an external observer, you never actually cross. Because of time dilation, you appear to slow down and fade away, your image becoming infinitely redshifted until you vanish. But from your perspective, you fall inward toward a destination where space and time are so warped that your physical form is crushed and assimilated into the mass of the whole. The paradox reached its most unsettling conclusion with the discovery of Hawking radiation. Stephen Hawking demonstrated that black holes are not truly permanent. They slowly leak radiation over trillions of years until they completely evaporate. This radiation, however, is thermal and random. It does not carry the data of what fell in. If you were the one who fell into the black hole, and that black hole eventually evaporated, the information that made you, your DNA, your memories, the arrangement of your atoms, would be gone. The universe would have effectively performed a delete command on a segment of reality. If information can be deleted, then the past is no longer secure. If the universe can forget the state of its particles, then the link between cause and effect is broken. We would be living in a universe where the present does not necessarily follow from the past. To resolve this, some physicists suggest the holographic principle. The idea that as you fall in, your information is actually smeared across the surface of the event horizon, preserved like a 2D encoded shadow, while your 3D body is destroyed. This implies that reality is not a solid three-dimensional volume, but a projection. It suggests that at the most fundamental level, you are not a collection of matter, but a collection of bits. If the information paradox remains unresolved, we must accept that either our understanding of gravity is fundamentally wrong, or the universe has the capacity to simply erase parts of itself without a trace. We are left looking at these dark abysses in space, realizing they may be the places where the ledger of reality is being systematically bleached of its content. The heat death and the arrow of time. You perceive time moving forward because entropy increases, meaning you are living through the slow, irreversible exhaustion of the universe's ability to do anything at all. This progression is dictated by the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time. In simple terms, energy naturally spreads out. It moves from concentrated, useful forms, like the nuclear fire of a star, to diffuse, useless forms, like the faint infrared glow of a cooling rock. Your life is only possible because you are caught in the middle of this transition, intercepting a stream of energy as it flows from a state of high order to a state of total chaos. The arrow of time is not a fundamental property of space, but a consequence of this decay. If you were to watch a video of two billiard balls colliding, the laws of physics would look the same whether the video played forward or backward. On a subatomic level, equations do not care about the direction of time. However, if you watch a video of a glass shattering, you instantly know which direction is forward. The shattered glass represents a state of higher entropy. The probability of the shards spontaneously reassembling is so low that it effectively never happens. This is the only reason you remember the past and not the future. You are a witness to the universe breaking. This process has a definitive, logical conclusion: the heat death. As stars burn through their hydrogen, they collapse into remnants, white dwarfs, neutron stars, or black holes. Eventually, even these remnants will fade. Over a period of 10 to the power of 100 years, the expansion of the universe will pull matter so far apart that galaxies will lose contact with one another. The very atoms that make up your body will eventually decay, if current theories of proton instability hold true. Even black holes will eventually vanish through the slow leak of Hawking radiation. Once the last black hole has evaporated, the universe will reach a state of maximum entropy. Every point in space will be exactly the same temperature, a fraction of a degree above absolute zero. There will be no light, no heat, and no gradients of energy. Without a difference in energy between 2 points, no work can be performed, no information can be processed, no thoughts can occur. In this state, time itself loses its meaning. Without change, there is no way to measure the passage of seconds or eons. The now becomes a permanent, unchanging state. You are living in the stelliferous era, a brief, high-energy anomaly in the history of the cosmos. This era is a mere flicker. For the vast majority of its existence, the universe will be a cold, dark, and static void. We find ourselves in a desperate race against a clock that cannot be wound back. Every star that ignites is a finite battery being drained. Every heartbeat you experience is an irreversible step toward a state where heartbeats are physically impossible. The universe is not a permanent home. It is an explosion in slow motion, and we are living in the moments before the smoke clears and the light goes out forever. The false vacuum decay. It is possible that the Higgs field, which gives you mass, is not in its lowest energy state, but is trapped in a false minimum that could collapse at any moment. To understand the gravity of this condition, you must first view the vacuum not as nothing, but as the foundational state of the universe's underlying fields. The Higgs field permeates every cubic centimeter of the cosmos. It is the invisible medium that provides resistance to elementary particles, manifesting as the property we call mass. The stability of all matter, the atoms in your lungs, the carbon in your bones, the light from the sun, depends entirely on the Higgs field maintaining a constant, predictable value. In physics, systems always seek the state of lowest possible energy, known as the true vacuum. Think of a ball sitting at the bottom of a valley. However, it is mathematically possible for a system to get stuck in a false valley. A dip in the landscape, that is, lower than its surroundings, but still higher than the absolute lowest point. This is a metastable state. It appears stable, and it may remain so for billions of years, but it is not the ultimate equilibrium. The unsettling reality is that our current measurements of the Higgs boson and the top quark suggest we are living in exactly such a state. We are inhabiting a false vacuum. This means the very fabric of our reality is top-heavy, possessing a latent energy that is waiting to be released. According to quantum mechanics, there is a phenomenon called quantum tunneling. Unlike a classical ball that needs a push to get over a hill and reach the lower valley, a quantum field can simply tunnel through the barrier. If this tunneling were to occur at any single point in the universe, it would trigger a catastrophic phase transition. A bubble of true vacuum would begin to expand outward from that point at the speed of light. Inside this bubble, the laws of physics would be fundamentally rewritten. The Higgs field would take on a different value, which means the masses of particles would change. Electrons might become too heavy to orbit nuclei. Atoms would dissolve. Gravity might behave in ways that prevent the formation of stars. Because the wall of this bubble travels at the speed of light, you would never see it coming. There is no signal that could outrun it to warn you. One moment, you are existing in a world of familiar chemical bonds and predictable forces. The next, the space you occupy is overwritten by a new, incompatible version of reality. Your body would not be destroyed in a traditional sense. It would simply cease to be a valid configuration of matter. The fundamental constants that allowed your molecules to hold together would vanish, and you would be rendered into a spray of alien particles in a fraction of a nanosecond. This is not a localized disaster. This bubble would continue to grow until it consumed the entire observable universe, erasing everything in its path and replacing it with a true vacuum that might be completely devoid of life or complexity. We have no way of knowing if such a bubble has already started forming in a distant galaxy. If it has, it is currently rushing toward us in total silence. We are living in a temporary bubble of stability, built upon a foundation that is mathematically destined to eventually collapse. The Fermi paradox and the great filter. The silence of the stars is not a lack of data, but a measurement of a void where there should be a signal, suggesting a recurring barrier that eliminates life before it can leave its home. When you look at the night sky, you are looking at a graveyard of potential. There are roughly 200 billion stars in our galaxy alone, and current observational data suggests that nearly every one of those stars hosts at least one planet. Many of these worlds are billions of years older than Earth. If the progression from basic chemistry to intelligent spacefaring civilization is a natural and common occurrence, the Milky Way should have been colonized millions of years ago. A civilization with even a fraction of our technological ambition, given a head start of a few million years, could have mapped the entire galaxy. Yet, when we point our most sensitive radio telescopes at the heavens, we hear nothing. This discrepancy is the Fermi paradox. It implies that there is a great filter, a developmental step or a catastrophic event that is so difficult to overcome that it prevents almost all life from reaching a state of interstellar visibility. This filter acts as a cosmic sieve, allowing only an infinitesimal fraction of life to pass through, or perhaps none at all. The terrifying nature of this concept lies not in the filter itself, but in its timing relative to us. If the great filter is behind us, we are the rarest of anomalies. It would mean that the jump from single-celled organisms to complex life, or the development of intelligence itself, is an almost impossible fluke. In this scenario, we are the only survivors of a brutal cosmic lottery, standing alone in a deserted theater. While this implies our survival for now, it places us in a position of extreme fragility, as there is no precedent for our continued existence. However, if the Great Filter is ahead of us, the implications are far more disturbing. It would suggest that many civilizations have reached our current level of technological maturity, developing radio communication, nuclear power, and orbital flight, only to hit a wall that inevitably leads to extinction. This could be an external threat, such as a recurring gamma-ray burst or a vacuum decay event, or it could be an inherent flaw in the nature of intelligence itself. Perhaps the very tools required to leave a planet, the mastery of high-density energy and advanced chemistry, inevitably lead to the destruction of the species that wields them. Every time we discover a potentially habitable exoplanet, or find evidence that Mars once had liquid water, the probability of the filter being ahead of us increases. If life is common, but intelligent civilizations are absent, then the barrier must lie somewhere between the two. The discovery of even a simple, extinct bacterial colony on another world would be the worst news we could receive. It would prove that life is not the filter, meaning the filter is something much more lethal, and it is still waiting for us in our future. The silence of the universe is a quantitative measurement of failure. It is the sound of billions of civilizations reaching for the stars and falling back into the dust. We are shouting into a dark forest, and the lack of a reply is not an absence of neighbors, but a warning of what happens to those who make too much noise, or those who simply do not survive long enough to speak. The holographic bound. Every object you touch and every three-dimensional volume you occupy may actually be a projection of information stored on a distant two-dimensional surface. This concept, known as the holographic principle, suggests that our perception of depth and the very space we inhabit is an architectural illusion. To understand this, we must look at the way information is stored in the universe. In your daily life, you assume that if you want to store more objects, you need a larger room, a greater volume. However, the laws of physics, specifically those governing black holes, reveal that the maximum amount of information you can cram into a space is not determined by its volume, but by its surface area. This realization began with the study of black hole event horizons. When an object falls into a black hole, the surface area of the event horizon increases. Physicists Jacob Bekenstein and Stephen Hawking discovered that the entropy, the information content, of a black hole is exactly proportional to the area of its event horizon. If you were to try and calculate the information capacity of a three-dimensional region of space, you would find that it cannot exceed the amount of information that can be written onto its two-dimensional boundary. Imagine a library. You would naturally assume that the number of books you can fit inside is limited by the cubic meters of the room. But the holographic principle suggests that the limit is actually dictated by the square footage of the walls. If you try to exceed this limit by adding more books, the room will eventually collapse into a black hole, and all the information contained within those books will be printed onto the surface of that black hole. This implies that the third dimension, the inside of the room, is not as fundamental as the two-dimensional surface that encloses it. This leads to a jarring conclusion about the nature of your own body and the world around you. If the information of the entire universe can be mapped onto a distant, two-dimensional boundary, then the three-dimensional bulk we experience is merely a projection of that data. You are familiar with the security holograms on credit cards. They appear to have depth and parallax, but they are physically flat. In this model, the real universe is a flat, two-dimensional sheet of quantum information located at the very edge of the cosmos, and everything you see, feel, and breathe is the three-dimensional hologram generated by that data. The implications for our understanding of reality are profound and unsettling. It suggests that the solid objects we interact with are secondary effects. The distance between you and the screen you are currently looking at might be a mathematical construct used by the universe to organize bits of information. If we were to zoom in deep enough, past the level of atoms and subatomic particles, we might find that the pixels of our reality are not three-dimensional voxels, but two-dimensional bits of information. We are forced to confront the possibility that space is not a container we live in, but a way for information to be presented to an observer. If you were to peel back the layers of your three-dimensional world, you wouldn't find more space. You would find a boundary. This suggests that the universe is not what it appears to be. We are living inside a projection, moving through a volume that may not exist in the way we have always assumed, governed by a source code that is written on a wall we can never reach. The quantum Zeno effect. By the mere act of observing a system, you can freeze its evolution, meaning the presence of a witness fundamentally alters the physical state of the measured object. This phenomenon, named after the Greek philosopher Zeno of Elea, suggests that the universe does not move or change in the way your intuition suggests. In your daily experience, you assume that a pot of water will eventually boil, whether you are looking at it or not. You believe that the world continues its mechanical progression behind your back. But in the quantum realm, the transition from one state to another is not a smooth, continuous slide. It is a probability that matures over time. If you interrupt that maturation by checking the system too frequently, you reset the clock. At the heart of this paradox is the wave function, the mathematical description of a particle's potential states. A radioactive atom, for instance, exists in a superposition of being both decayed and undecayed. As time passes, the probability of it decaying increases. However, according to the standard Copenhagen interpretation of quantum mechanics, the act of measurement forces the wave function to collapse into a single, definite state. If you measure the atom and find it has not yet decayed, you have forced it back into its original state of being undecayed, with 100% certainty. The quantum Zeno effect occurs when these measurements are performed so rapidly that the system never has the chance to move. By observing the particle at incredibly short intervals, you effectively trap it in its starting position. Mathematically, for a very short period after a measurement, the probability of a particle transitioning to a new state grows quadratically, meaning it starts off very slowly. If you look again before the probability has gained enough momentum, you collapse it back to zero. You are, quite literally, preventing reality from unfolding simply by insisting on knowing what it is doing. This has been verified in laboratory settings using laser-cooled ions. By repeatedly hitting atoms with pulses of light, the observation, scientists have successfully prevented them from transitioning between energy levels, even though the transition was energetically scheduled to happen. The implications are quietly disturbing. It suggests that the flow of time and the evolution of matter are not independent processes. They are deeply entangled with the presence of an observer. If the universe is composed of quantum particles, then the stability of the entire cosmos may be a product of constant interaction. This raises a difficult question. What counts as an observer? In physics, a measurement doesn't require a human mind. It only requires an interaction with an external environment that extracts information. This means that the universe is constantly measuring itself. Particles bouncing off one another, light hitting dust, heat radiating into the void. This continuous checking may be the only thing keeping the universe from dissolving back into a chaotic blur of infinite probabilities. However, if we take this to its logical conclusion, it implies that the solidity of your world, the fact that your chair remains a chair and the moon remains in its orbit, is maintained by a relentless cycle of measurement. We are forced to consider a reality where change is not an inherent property of matter, but a permission granted by the absence of a witness. When you turn your head, you are allowing the world behind you to resume its probabilistic dance, only to freeze it back into a single, rigid state the moment you look back. The KBC void and the density conflict. We appear to live inside a massive, underdense region of space that contradicts our standard model of how matter should be distributed across the cosmos. This region, named the KBC void after astronomers Keenan, Barger, and Cowie, is estimated to be roughly 2 billion light-years in diameter. To put this in perspective, this is the largest void ever identified in the known universe, and we are sitting almost directly in the center of it. According to the standard model of cosmology, the universe should be homogeneous on such a vast scale. The density of galaxies and matter in our local neighborhood should, statistically, be the same as any other patch of the sky. Yet, our measurements show that the density of our local environment is 30% to 40% lower than the cosmic average. This is not a mere astronomical curiosity. It is a structural anomaly that threatens to invalidate our most basic assumptions about the age and expansion of the universe. When we measure how fast the universe is growing, we use a value called the Hubble constant, h0. However, we have a problem. When we look at the distant cosmic microwave background radiation, the light from the beginning of time, the math tells us the universe is expanding at a certain rate. But when we look at local objects, like nearby supernovae, they appear to be moving away from us much faster. The KBC void provides a potential, albeit unsettling, explanation for this Hubble tension. If we are living in a massive, empty bubble, the surrounding regions of higher density would exert a gravitational pull on everything inside. Like a vacuum drawing in air, the denser outer edges of the void would pull our local galaxies outward, making it appear as though the universe is expanding faster than it actually is. In this scenario, our local measurements are not a reflection of the true cosmic expansion, but a result of our unique and precarious position within a cosmic wasteland. However, the existence of a void this large is itself a violation of the rules. The standard lambda CDM model, the prevailing theory of how the universe evolved, predicts that gravity simply there is a definitive edge to what you can see, and every second, distant galaxies are crossing that line, vanishing forever into a region of space that is moving away from you faster than light. This boundary is known as the particle horizon. It is the maximum distance from which light could have traveled to reach your eyes since the beginning of time. Because the universe has a finite age, 13.8 billion years, there is a limit to how much of the cosmos has had enough time to reveal itself to us. Beyond this sphere, the universe may be infinite, But for all practical and physical purposes, those regions do not exist in your reality. They are outside your causal reach. This limit is not static, nor is it merely a result of distance. It is dictated by the expansion of space itself. According to general relativity, space is not a fixed stage. It is a flexible fabric that can stretch. While no object can travel through space faster than the speed of light, the fabric of space itself can expand at any rate it chooses. In the distant reaches of the cosmos, the cumulative effect of this expansion means that the gap between us and far-off galaxies is growing faster than 299,792 kilometers per second. When a galaxy crosses this threshold, it enters a region where its light can no longer bridge the widening gap. To you, the observer, that galaxy will appear to grow dimmer and redder as its light waves are stretched to infinite wavelengths. Eventually, it will fade into a frozen ghost and then vanish entirely. This is not a temporary obscuration, it is a permanent severance. Once a galaxy passes the cosmological event horizon, no signal, no message, and no physical probe can ever reach it, even if we were to travel at the speed of light for an eternity. The most unsettling aspect of this measurement is the realization that the observable universe is shrinking in terms of its content. Even though the horizon itself expands as light has more time to travel, the accelerating expansion of the universe, driven by dark energy, is pushing matter away faster than the horizon can grow to catch it. We are in a race against the stretching of the void, and we are losing. Currently, we can observe roughly 2 trillion galaxies, but every day, approximately 20,000 stars pass beyond the limit of our sight. We are living in a cosmic island that is slowly being evacuated. If you were to wait long enough, trillions of years, every galaxy outside our immediate local group would have crossed this line. The sky would eventually become a true void, devoid of the distant light that told us we were part of a larger whole. This implies that our current understanding of the universe's scale and history is a luxury of our specific time. We are privileged to see the clues of the Big Bang and the distribution of matter across the deep field. Future observers will see nothing but an empty black sky, and they will have no empirical reason to believe that other galaxies ever existed. We are watching a slow-motion vanishing act, forced to accept that the vast majority of the universe has already left us, and the rest is following it into a darkness that we are physically incapable of ever penetrating again. It's not had enough time since the Big Bang to clear out a hole of this magnitude. Matter should be more evenly distributed. For a void 2 billion light-years wide to exist, our understanding of how gravity works on a cosmic scale, or our understanding of dark matter, must be fundamentally incomplete. It suggests that the smooth universe we see in our equations is an idealized fiction. This leaves us with a disturbing possibility. We are observing the cosmos from an atypical vantage point. Most of our fundamental truths about the universe, its age, its composition, and its ultimate fate, are derived from observations made from within this underdense anomaly. If our local yardstick is warped by the unique geometry of the KBC void, then our map of the entire universe is based on a skewed perspective. We are like a traveler standing in a rare, empty clearing in the middle of a dense forest, assuming the rest of the world is also a clearing. The data suggests that the real universe, the one outside our 2 billion light-year bubble, may be far denser and behaving under different gravitational pressures than what we experience here. We are forced to wonder if our physics is truly universal, or if we have merely mastered the laws of a very large, very empty room. The particle horizon and the limits of sight. There is a definitive edge to what you can see, and every second distant, galaxies are crossing that line, vanishing forever into a region of space that is moving away from you faster than light. This boundary is known as the particle horizon. It is the maximum distance from which light could have traveled to reach your eyes since the beginning of time. Because the universe has a finite age, roughly 13.8 billion years, there is a limit to how much of the cosmos has had enough time to reveal itself to us. Beyond this sphere, the universe may be infinite, but for all practical and physical purposes, those regions do not exist in your reality. They are outside your causal reach. This limit is not static, nor is it merely a result of distance. It is dictated by the expansion of space itself. According to general relativity, space is not a fixed stage. It is a flexible fabric that can stretch. While no object can travel through space faster than the speed of light, the fabric of space itself can expand at any rate it chooses. In the distant reaches of the cosmos, the cumulative effect of this expansion means that the gap between us and far-off galaxies is growing faster than 299,792 kilometers per second. When a galaxy crosses this threshold, it enters a region where its light can no longer bridge the widening gap. To you, the observer, that galaxy will appear to grow dimmer and redder as its light waves are stretched to infinite wavelengths. This is not a temporary obscuration. It is a permanent severance. Once a galaxy passes the cosmological event horizon, no signal, no message, and no physical probe can ever reach it, even if we were to travel at the speed of light for an eternity. The photons emitted by those stars today will simply never have enough speed to overcome the increasing amount of space being created between us. The most unsettling aspect of this measurement is the realization that the observable universe is shrinking in terms of its accessible content. Even though the horizon itself technically expands as light has more time to travel, the accelerating expansion of the universe, driven by dark energy, is pushing matter away faster than the horizon can grow to catch it. We are in a race against the stretching of the void, and we are losing. Currently, we can observe roughly 2 trillion galaxies, but every day, thousands of stars pass beyond the limit of our sight. We are living in a cosmic island that is slowly being evacuated. If you were to wait long enough, hundreds of billions of years, every galaxy outside our immediate local group would have crossed this line. The sky would eventually become a true void, devoid of the distant light that told us we were part of a larger whole. This implies that our current understanding of the universe's scale and history is a luxury of our specific time. We are privileged to see the clues of the Big Bang and the distribution of matter across the deep field. Future observers will see nothing but an empty, black sky, and they will have no empirical reason to believe that other galaxies ever existed. We are watching a slow-motion vanishing act, forced to accept that the vast majority of the universe has already left us, and the rest is following it into a darkness that we are physically incapable of ever penetrating again. The neutrino floor. Trillions of nearly massless particles are passing through your body every second without interaction, revealing a ghost-like layer of reality that you are physically incapable of feeling. These are neutrinos, subatomic particles produced by nuclear reactions in the heart of the Sun, the decay of radioactive elements in the Earth's core, and the distant, violent deaths of stars. They are often called ghost particles because they lack an electric charge and possess such a minuscule mass that they rarely interact with the electromagnetic forces that govern your world. To a neutrino, your body, your house, and the entire planet are not solid barriers. They are vast, empty spaces. You perceive the world as a place of solid boundaries and physical contact. When you touch a surface, the electrons in your hand repel the electrons in the object, creating the sensation of resistance. But neutrinos do not feel this repulsion. They move through the solid Earth as easily as a bird flies through a cloud. At any given moment, about 65 billion neutrinos are passing through every square centimeter of your skin. If you were to build a wall of lead 1 light-year thick, a neutrino would still have a 50% chance of passing through it without hitting a single atom. This leads to a profound observational limit in our search for the hidden components of the universe. We are currently building hypersensitive detectors deep underground, in abandoned mines and under mountains, to search for dark matter. These detectors are designed to catch the extremely rare moment when a dark matter particle strikes an atom. However, as our technology becomes more sensitive, we are approaching a barrier known as the neutrino floor. At this level of precision, the sheer volume of solar and atmospheric neutrinos creates a noise that is indistinguishable from the signals we are looking for. The neutrino floor represents a fundamental limit to our vision. It is a point where the background radiation of the universe becomes so thick that we can no longer see the ghosts we are hunting. But the existence of this floor also forces us to confront the limitations of our biological perception. We evolved to survive in a world of macroscopic objects, predators, food, and terrain. Our senses are tuned to a very narrow frequency of reality. The fact that 1 trillion particles can pass through your brain without leaving a trace is a reminder that you are essentially a phantom in a much more crowded universe. If we could see neutrinos, the sky would not be dark at night. The sun would glow through the earth beneath your feet, and the entire atmosphere would be a shimmering haze of cosmic radiation. We are living in a dual reality, one that is solid and tangible, and another that is fluid and pervasive, passing through us with total indifference. This ghost layer is not a theoretical abstraction. It is a measurable, physical presence that proves the majority of what is happening in the room with you right now is completely beyond your ability to sense or influence. We are left with the realization that our definition of existence is purely a matter of interaction. We believe things are real because they push back against us. But neutrinos prove that something can be undeniably present, carrying energy and information across the cosmos, while remaining entirely untouchable. We are standing on a floor made of ghosts, oblivious to the storm of particles that defines the true density of the space we inhabit. The CMB cold spot. In the map of the early universe's radiation, there is a massive area of unexplained coldness that suggests our universe may have collided with another. This map, known as the Cosmic Microwave Background, CMB, is the oldest light in the cosmos, a snapshot of the universe as it existed 380,000 years after the Big Bang. It is a merely uniform glow of microwave radiation, but it is speckled with tiny temperature fluctuations that represent the seeds of future galaxies. Most of these fluctuations are predictable, following a Gaussian distribution of hot and cold spots. However, In the southern celestial hemisphere, there is a vast, anomalous region known simply as the cold spot. It is roughly 1.8 billion light-years across and significantly colder than the statistical models of the Big Bang allow. According to the standard inflationary model, the distribution of matter and energy in the early universe should be random but even. While small cold spots are expected, the sheer scale and intensity of this specific void defy the odds of 1 in 50. It is too large and too empty to be the result of a standard fluctuation. To explain its existence, astronomers first looked for a supervoid, a region of space where there are simply fewer galaxies, causing light to lose energy as it passes through. But even the largest identified supervoids cannot account for the temperature drop we measure in the CMB cold spot. The math does not reconcile. This leaves us with several unsettling possibilities that challenge the idea of our universe as a self-contained system. One of the leading, albeit controversial, theories is that the cold spot is a bruise on the fabric of space-time. If our universe is just one bubble in a larger, eternal multiverse, it is possible that another bubble universe collided with ours during the period of cosmic inflation. Such a collision would have left a permanent signature in the CMB, a distortion caused by the interaction of two different realities. In this view, the cold spot is not a part of our universe's internal history, but a scar from an external encounter. If this is true, the implications are staggering. It would mean that the observable universe is not the totality of existence, but merely a localized fragment of a much larger and more chaotic landscape. It would mean that the laws of physics we have derived from our observations might be specific only to our bubble, and that beyond the cold spot, there are regions where gravity, time, and the very nature of matter operate under entirely different constraints. The cold spot becomes a window into a beyond that we are otherwise physically incapable of perceiving. The existence of such a scar suggests that our universe is not a closed circuit. We are forced to consider that the Big Bang was not necessarily a singular, isolated event, but one of many. Every measurement we take of the cold spot reminds us that we might be living in the aftermath of a cosmic impact, a realization that renders our entire galaxy a tiny, vulnerable speck in a sea of colliding infinities. We are observing the thermal residue of a contact with the unknown, a measurement that suggests our universe is not alone, but is instead part of a vast, crowded, and potentially violent ecology of worlds. The cold spot remains an open wound in the side of modern cosmology. It is a reminder that there are features of our reality that cannot be explained by looking inward. As we continue to refine our maps of the early universe, this anomaly stands as a silent testimony to the possibility that we are not the masters of a singular reality, but residents of a bruised bubble drifting through a multiverse we are only beginning to imagine. The measurement problem. In the quantum realm, a particle does not have a definite position until you look at it, implying that the solidity of your world is a product of interaction rather than an inherent property of matter. This is the central crisis of quantum mechanics. We often imagine atoms as tiny solar systems with solid balls of matter orbiting a nucleus. But the reality revealed by the double-slit experiment and nearly a century of subsequent testing is much more fluid. Before a measurement is made, a particle exists as a wave of probability, a mathematical blur that occupies multiple positions simultaneously. This state is known as superposition. It is not that the particle is simply hidden from us. It is that the particle has not yet decided where to be. The moment an observer, or a measuring device, interacts with the particle, this wave function collapses. The blur vanishes, and the particle appears in a single, localized spot. This leads to the measurement problem. Why does the act of looking change the fundamental nature of reality? There is nothing in the Schrödinger equation, the formula that describes how these waves evolve, that explains how or why a collapse occurs. The math suggests that the wave should simply continue to spread out forever. Yet, your every experience tells you that the world is composed of distinct, solid objects in fixed locations. This creates a logical chasm. If you are made of atoms, and atoms are quantum objects that exist in states of probability, then you too should exist in a state of superposition. By extension, the chair you sit on and the planet you inhabit should be a shimmering haze of possibilities rather than concrete things. We are forced to ask where the quantum world ends and the real world begins. We have searched for a Heisenberg cut, a specific scale or mass where the rules of probability give way to the rules of certainty, but we have never found it. We have seen larger and larger molecules containing thousands of atoms being coerced into behaving like waves. One unsettling interpretation of this problem is that the universe is not actually there when we aren't looking. This is the objective reduction challenge. If no measurement occurs, the universe remains a featureless cloud of overlapping potentials. It implies that reality is a collaborative construction, a consensus reached only through the constant, relentless interaction of particles. Your sense of a stable, objective world exists only because the environment is constantly measuring itself. Photons bouncing off surfaces, air molecules colliding with walls, forcing the wave functions of the macroscopic world to remain in a state of perpetual collapse. However, if we follow the math without assuming a collapse, we arrive at the many worlds interpretation. In this view, the wave function never collapses. Instead, when you measure a particle, you become entangled with it. The universe splits. In one branch, you see the particle here. In another, you see it there. If this is true, then the solidity you perceive is an illusion caused by your confinement to a single branch of an infinitely branching tree. You are not seeing a definite world. You are simply one version of yourself witnessing one possible outcome of a trillion daily quantum coin tosses. We are left with a fundamental disconnect between our math and our senses. We have built our entire civilization on the reliability of matter, yet at the deepest level we can probe, that reliability disappears. We cannot explain how a world of maybe becomes a world of is. We are forced to consider that the ground beneath our feet is a mathematical afterthought, a byproduct of an observational process we do not yet understand, existing only because we, or the universe itself, refuse to stop looking. The dark matter ghost. The vast majority of the gravity holding your galaxy together comes from a substance that does not reflect, emit, or absorb light, and which remains undetectable to every sensor we have built. This is dark matter, a term that serves more as a confession of our ignorance than a description of a known material. When we observe the Milky Way, we calculate the mass of every star, every planet, and every cloud of gas. Based on the laws of Newtonian gravity and general relativity, this visible matter does not provide nearly enough gravitational pull to keep the galaxy intact. At the speeds they are traveling, the stars on the outer edges of the galaxy should be flung out into intergalactic space, like drops of water spinning off a wet tire. Yet, they remain in place. They behave as if they are embedded in a massive, invisible scaffolding. When we look at the cosmic scale, the discrepancy becomes even more alarming. By measuring the way light from distant galaxies is bent by gravity, a phenomenon called gravitational lensing, we can weigh the universe. The results are consistent. The matter we can see, the matter made of atoms and light, accounts for only about 5% of the total energy density of the universe. Roughly 27% is dark matter, and the rest is dark energy. You and everything you have ever seen are a minor impurity in a universe dominated by a ghost. This substance is not merely dark in the sense that it is unlit. It is fundamentally transparent to the electromagnetic force. It does not interact with light at all. If you were to hold a sphere of dark matter in your hand, you would see nothing, and it would pass through your palm as if it were not there. It occupies the same space as the air in your room, passing through your brain and the core of the earth without friction or collision. We only know it exists because it possesses mass, and therefore it exerts gravity. It is a one-way interaction. It can pull on us, but we cannot touch, see, or hear it. For decades, physicists have constructed elaborate traps to catch a single particle of dark matter. We have built detectors kilometers underground to shield them from cosmic rays, using vats of liquid xenon and supercooled crystals, waiting for a single, anomalous nudge from a dark matter candidate, like a WIMP, a weakly interacting massive particle. Thus far, the silence is absolute. Every experiment has come up empty. We are chasing a phantom that dictates the architecture of the cosmos but refuses to acknowledge our existence. The implications of this measurement are quietly disturbing. It suggests that our mastery of the electromagnetic spectrum, the foundation of all modern technology and science, is only giving us a glimpse into a tiny, atypical fraction of reality. We are like deep-sea creatures living near a volcanic vent, unaware of the vast, open ocean above us because we lack the organs to perceive it. The real business of the universe, the gravitational tug-of-war that forms galactic filaments and cosmic voids, is being conducted by a substance that is entirely alien to our chemistry. We are forced to exist in a world where the primary architect is invisible. Your galaxy is not a collection of stars. It is a massive, dark halo in which a few sparks of visible light have happened to settle. We are the exceptions, the outliers, the 5% that happens to glow. We are left to wonder if this dark sector has its own complex physics, its own unseen structures, or even its own forms of life that are just as oblivious to us as we are to them. We are residents of a haunted house, feeling the floorboards creak under the weight of something we can never look in the eye. The expansion, H0 tension. The two primary ways we measure the expansion of the universe give two different, irreconcilable results, suggesting a fundamental flaw in our understanding of cosmic history. This discrepancy centers on a single number, the Hubble constant, H0. This value represents the rate at which the universe is stretching, a measurement that should, in theory, be the most robust and reliable figure in all of cosmology. It tells us how fast a galaxy is receding from us based on its distance. Yet, as our instruments have become more precise, the data has not converged on a single answer. Instead, it has split into two distinct camps that refuse to meet, creating a crisis that threatens the very foundation of the standard model of cosmology. The first method is the early universe approach. By observing the cosmic microwave background, CMB, the ancient light emitted when the universe was only 380,000 years old, physicists can use our best models of physics to predict how fast the universe should be expanding today. This method, spearheaded by the Planck satellite, yields a value of approximately 67 kilometers per second per megaparsec. This number is based on a deep understanding of the initial conditions of the Big Bang, the distribution of matter, and the influence of dark energy over 13.8 billion years. It is a mathematical extrapolation of the past into the present. The second method is the local universe approach. This involves looking at the universe as it is now. Astronomers use standard candles, such as Cepheid variable stars and Type 1a supernovae, to build a cosmic distance ladder. By measuring the brightness and redshift of these objects in nearby galaxies, calculate the expansion rate directly. This method, most notably associated with the Hubble Space Telescope and more recently the James Webb Space Telescope, consistently yields a value of approximately 73 kilometers per second per megaparsec. A difference of 6 units may seem small, but in the context of precision cosmology, it is an unbridgeable chasm. The statistical significance of this tension has reached what scientists call 5 sigma, meaning there is less than a 1 in a million chance that this is a simple measurement error. This is no longer a matter of refining our tools. It is a signal that something is fundamentally wrong with our map of reality. If the local measurement is correct, then the universe is expanding faster than our theories of the Big Bang allow. This would mean that our model of how the universe evolved from its infancy to the present day is missing a crucial piece of physics. Perhaps dark energy is not a constant, but something that changes over time. Perhaps there is an undiscovered species of subatomic particle, like a sterile neutrino, that exerted extra pressure in the early universe. Or perhaps gravity itself does not behave the way Einstein predicted over vast cosmic distances. The unsettling implication is that we do not understand the history of the space we inhabit. We are like historians who have a perfect record of a civilization's birth and a perfect record of its current state, but whose records show that the civilization should be 1,000 miles away from where it actually sits. The H0 tension suggests that there is a dark epoch in cosmic history, an era where the rules changed, or where a force we have yet to name accelerated the stretching of the void. We are forced to admit that our standard model of the universe may be a localized approximation that is now failing to account for the true, unsettling nature of cosmic expansion. The anthropic coincidence. The physical constants of nature, the strength of gravity, the charge of an electron, appear to be precisely calibrated for life, a fact that suggests we are either an impossible fluke or a calculated outcome. This observation is not born of a desire for cosmic significance, but from the rigid, uncompromising numbers that govern the subatomic and cosmological realms. There are approximately 26 dimensionless physical constants in the standard model of physics, numbers that are not derived from any deeper theory, but are simply input by the universe. If any of these values were to deviate by a fraction of a percentage, the mechanical processes that lead to the formation of stars, the synthesis of carbon, and the stability of DNA would cease to function. Take, for example, the strong nuclear force which binds protons and neutrons together in the nucleus of an atom. If this force were only 2% stronger, 2 protons would be able to fuse easily, creating a universe where all hydrogen, the primary fuel for stars, was consumed in the first few minutes of the Big Bang. There would be no long-lived stars and no water. If the force were 5% weaker, the nuclei of essential elements like carbon and oxygen would be unstable. They would simply fly apart. You are composed of heavy elements that were forged in the hearts of dying stars, a process that relies on a specific resonance in the carbon atom known as the Hoyle state. This state exists at an energy level so precise that its occurrence seems mathematically absurd. Yet, without it, the universe would be a graveyard of hydrogen and helium. The same precision applies to the expansion rate of the universe and the strength of gravity. If gravity was slightly stronger, the universe would have collapsed back onto itself long before the first planet could form. If it was slightly weaker, matter would have spread out too thinly to ever coalesce into galaxies. We find ourselves in a Goldilocks universe, where every dial has been turned to the exact setting required for complexity to emerge from chaos. This is the heart of the anthropic coincidence. The universe looks as if it knew we were coming. There are 2 primary ways to interpret this measurement, and neither is comfortable. The first is the multiverse hypothesis. It suggests that there are an infinite number of universes, each with a different set of physical constants. Most of these universes are stillborn, dark, empty, or collapsed. We simply happen to find ourselves in the one where the numbers work, much like a survivor of a plane crash might wonder at the miracle of their luck while ignoring the thousands of flights that ended in disaster. This reduces our existence to a statistical inevitability in an infinite sea of failure. The second interpretation is even more unsettling, that the universe is not a random accident. If the laws of physics are not a fluke, then they are a prescription. This does not necessarily imply a conscious creator in the traditional sense, but it suggests that the ground state of reality is biased toward the creation of observers. It implies that mind and matter are not separate, but that the universe is a system that requires an observer to finalize its own properties. We are left to wonder if the universe is as it is because we are here to see it, or if we are here because the universe could be no other way. The data does not offer a resolution. It only confirms that the boundary between life and non-existence is a mathematical line so thin it should have been crossed by accident eons ago. We are standing on a peak of impossibility, looking down into a void of failed realities where the numbers simply refused to add up. The end of causality in entanglement. 2 particles can be linked such that a change to one instantly affects the other across the universe, bypassing the speed of light and the very concept of before and after. This is quantum entanglement, a phenomenon that Albert Einstein famously dismissed as spooky, action at a distance. In a classical world, if you want to influence an object, you must interact with it. You must send a signal, a wave, or a particle to bridge the gap. This interaction is limited by the universal speed record, the speed of light. Because of this limit, causality is preserved. If a star on the other side of the galaxy explodes, you cannot know about it, and it cannot affect you for tens of thousands of years. There is a comfortable delay between cause and effect. In the quantum realm, this delay vanishes. When 2 particles become entangled, they cease to be two independent entities. They become a single, unified system described by a single wave function, regardless of the physical distance between them. If you take a pair of entangled photons and separate them by the width of a galaxy, they remain fundamentally connected. When you measure the spin of one particle, its state is determined instantly, and at that exact same moment, its partner across the void assumes the corresponding state. This is not a matter of the particles sending a signal to each other. If they were communicating, the signal would have to travel billions of times faster than light, violating the core tenets of relativity. Instead, the measurement reveals a non-local reality. It suggests that the space between the particles, the thousands of light years of vacuum, is an illusion. On a fundamental level, the particles are still touching. The distance we perceive is a property of the macroscopic world that does not exist in the underlying code of the universe. The implications for causality are devastating. In our daily lives, we rely on the sequence of events. A happens, then B happens. But if two events are linked instantaneously across space, the order of those events becomes subjective. Depending on your frame of reference and how you are moving through space-time, one observer might see particle A change before particle B, while another observer sees particle B change before particle A. In an entangled system, there is no absolute first. The concept of a cause preceding an effect is dissolved into a simultaneous correlation. This violates the principle of locality, the idea that an object is only influenced by its immediate surroundings. If the universe is non-local, then everything in the cosmos could, in theory, be entangled with everything else. The atoms in your brain could be linked to particles at the edge of the observable horizon, reacting to measurements that occurred in a region of space you can never see. You are not an isolated system. You are a node in a vast, invisible web of instantaneous influence. We are left with a reality that is fundamentally fragmented. Our math works perfectly, and our experiments consistently confirm that entanglement is real. Yet we cannot reconcile it with our experience of time and space. We live in a world that appears to follow the rules of here and now, while the very particles we are made of operate in a realm where here and there are identical, and before and after have no meaning. The universe is not a collection of separate parts. It is a single, interconnected fabric that only pretends to be divided by the distances we see. The loneliness of the local group. Gravity has already lost the war against expansion on a large scale, meaning that eventually, every galaxy outside our immediate cluster will disappear, leaving us in a truly empty universe. This is the inevitable conclusion of a universe dominated by dark energy. While gravity is powerful enough to hold together planets, solar systems, and even small groups of galaxies, it is a short-range force compared to the relentless, repulsive push of the vacuum. On the largest scales, the universe is not just expanding, that expansion is accelerating. We are currently living in a brief window of cosmic history where the light from distant clusters can still reach us, but that window is slamming shut. Our local group is a small collection of about 50 galaxies, dominated by the Milky Way and Andromeda. Within this small pocket, gravity is winning. In about 4 billion years, the Milky Way and Andromeda will collide and merge into a single, massive elliptical galaxy. However, while we are busy merging with our neighbors, the rest of the universe is being stripped away. The vast filaments of the cosmic web, which connect us to thousands of other galaxy clusters like the Virgo supercluster, are being stretched to the breaking point. The terrifying reality of this cosmic isolation is that it is irreversible. Because the expansion of space is accelerating, the distance between the local group and the next nearest cluster is growing faster than the speed of light. This means that even if we were to develop a spacecraft that could travel at 299,792 kilometers per second, we could never leave our local neighborhood. Every other structure in the universe is effectively moving into our future's past, a region of space-time that is forever inaccessible to us. As time progresses, the cosmological event horizon will draw closer and closer. One by one, the distant galaxies that currently fill our telescopes will redshift into invisibility. Their light will be stretched until its wavelength is longer than the diameter of the observable universe, rendering them undetectable. To a future astronomer living in the merged Milky Way Andromeda galaxy 1 trillion years from now, the sky will look fundamentally different. The thousands of galaxies we see today in the deep field images will be gone. There will be no cosmic microwave background to study, and no evidence of the Big Bang. These future observers will be trapped in a dark sky paradox. They will look out into a total, absolute void. Without the light of distant galaxies to measure, they will have no way of knowing that the universe is expanding. They will likely conclude that their single galaxy is the entirety of existence, a lone island of matter in an infinite, eternal, and static darkness. We are the last generation of observers who can see the big picture. We are witnesses to a cosmic tapestry that is being systematically unraveled. This loneliness is the ultimate fate of all matter. The Big Freeze, or heat death, is often discussed as a matter of temperature, but its most haunting aspect is the social isolation of the cosmos. The universe began with a moment of total connection, where every particle was in contact with every other. Since that moment, the history of the universe has been a story of increasing separation. We are drifting apart, not just as individuals or societies, but as entire galactic civilizations. We are moving toward a state where the only things we can ever know are the things we can touch, while the vast majority of reality vanishes behind a horizon we can never cross. The Iron Star Era. In the far future, after all stars have died, cold fusion will slowly turn all remaining matter into iron, leaving the universe a graveyard of cold, black spheres. This era represents the absolute twilight of matter itself, occurring on a timescale so vast that it dwarfs the current age of the universe to the point of insignificance. We are currently living in the Stelliferous era, a time of vibrant energy and light, but this is a mere blink in the total lifespan of the cosmos. When the last red dwarf star finally exhausts its fuel and fades into a black dwarf, the universe will enter a period of profound darkness. Yet, even in this darkness, the laws of physics will continue to work, slowly reshaping every solid object that remains. The engine behind this transformation is quantum tunneling. In our current era, nuclear fusion requires the immense heat and pressure found in the cores of stars to overcome the electrical repulsion between atoms. However, at temperatures near absolute zero, a process called cold fusion, or pycnonuclear fusion, takes over. Over eons, the atoms within dead stars and frozen planets will occasionally tunnel through their energy barriers, fusing into heavier elements. This process always moves toward the most stable nucleus in the universe, iron 56. Iron sits at the bottom of the energy well. It is the point where you can no longer gain energy from fusion or fission. This transition is not fast. It is estimated to take between 101,500 and 102,600 years. Numbers so large, they defy human comprehension. To visualize this, imagine a grain of sand representing the entire 13.8 billion years of history since the Big Bang. To reach the Iron Star era, you would need a desert of sand that spans the entire observable universe. During this unthinkable span of time, every derelict spacecraft, every frozen asteroid, and every dead cinder of a star will slowly, atom by atom, transmute into solid, cold iron. The universe will become a collection of iron stars, massive, dark spheres that are perfectly uniform in composition. These iron spheres will be the final monuments of a universe that once hosted life, light, and complexity. They will be cold to the touch of the vacuum, emitting no light and possessing no internal heat. They are the ultimate dead ends of chemistry. In this era, the concept of a chemical reaction or biological process will be a physical impossibility. There is no more potential energy to be harvested. The universe will have reached its chemical equilibrium, a state where nothing can ever happen again because every atom has reached its most stable possible form. However, even the Iron Star era is not the final chapter. If protons are unstable, a possibility predicted by many grand unified theories, then these iron stars will eventually begin to evaporate. Over a period of 1,030 to 10,200 years, the very subatomic particles that make up the iron will decay into positrons and photons. One by one, the iron stars will dissolve into radiation, bleeding away into the expanding void until not a single speck of matter remains. The Iron Star era is the universe's final attempt at structure. It is the period where the cosmos gathers all its remaining stuff and organizes it into the most stable configuration possible before surrendering to the void. It serves as a haunting reminder that matter is not a permanent fixture of reality. It is a temporary state of condensed energy that is slowly being filtered through the sieve of time. We are living in the era of fire and liquid water, but we are headed toward an era of cold, silent iron, the last solid objects in a universe that is preparing to forget it ever existed. The problem of now. Einstein's relativity proves that there is no universal now, meaning that your present moment is entirely subjective and has no special status in the fabric of space-time. To our human intuition, the now feels like a moving spotlight, a shared experience that connects everyone on Earth, and perhaps everyone in the galaxy, in a single, simultaneous pulse of existence. We imagine the past is gone, the future is yet to be, and the present is the only thing that is truly real. But physics tells a different story. According to special relativity, simultaneity is relative. If two events happen at the same time for you, an observer moving at a different velocity will see them happen at different times. Neither of you is wrong. There is simply no objective, true time to adjudicate the disagreement. This breakdown of a shared present is a direct result of the fact that space and time are not separate entities, but are woven together into a four-dimensional manifold called space-time. In this framework, the speed of light is the only constant. Because the speed of light is fixed, space and time must stretch and contract to accommodate different observers. This leads to the Andromeda paradox. Imagine two people walking past each other on a sidewalk. Because they are moving at slightly different speeds, their planes of simultaneity, what they would consider to be now, are tilted at different angles. For one person, the now in the Andromeda galaxy might include a fleet of alien ships launching an invasion. For the person walking the other way, that same now might correspond to a time on Andromeda days or even weeks before the fleet was even built. If there is no universal now, then the distinction between the past, the present, and the future becomes a persistent illusion. This leads many physicists to the block universe theory, or eternalism. In this model, the universe is a four-dimensional block where every moment in time exists simultaneously. Your birth, your first day of school, the moment you are reading this sentence, and your eventual death are all equally present at their specific coordinates in the space-time block. Time does not flow any more than a highway flows. You are simply an observer moving along a specific path through the time structure. This perspective destroys our conventional understanding of causality and free will. If the future already exists as a fixed coordinate in the block, then the idea that we are creating the future through our choices is a misunderstanding of our perspective. We perceive a flow of time because of the way our brains process entropy and memory. But this is a psychological phenomenon, not a physical one. We are like passengers on a train looking out the window. Just because we have passed a house doesn't mean the house has ceased to exist. And just because we haven't reached the next station doesn't mean it isn't already there. The problem of now also complicates our understanding of the universe's beginning and end. If all time exists as a single block, the Big Bang is not an event that happened long ago in a way that makes it less real than today. It is simply one edge of the block. Similarly, the end of the universe is just the other edge. There is no special, current moment moving between them. We are left with a reality that is static and eternal, where every moment of joy and every moment of suffering is permanently etched into the geometry of the cosmos. We find ourselves trapped in a sensory experience that contradicts the fundamental math of the universe. We feel the urgency of the present, the regret of the past, and the anxiety of the future. Yet the stars in the vacuum do not recognize these categories. We are residents of a four-dimensional landscape, desperately trying to interpret a frozen masterpiece as if it were a moving film. Our now is not the heartbeat of the universe. It is merely the point where our specific story happens to be intersecting with the infinite. The proton decay uncertainty. If the proton is not eternal, then the very building blocks of your DNA have an expiration date, and all matter in the universe will eventually dissolve into radiation. This is one of the most haunting possibilities in modern physics. For decades, we have treated the proton as a fundamental, indestructible pillar of reality. It is the heart of every atom. Its stability ensures that the carbon in your cells and the oxygen in the atmosphere remain as they are for billions of years. But many grand unified theories, GUTs, which seek to unite the fundamental forces of nature, suggest that the proton's reign is not infinite. They predict that, given enough time, the proton will eventually fail. The mechanism of this failure is a process where the quarks that make up a proton transform into lighter particles, such as positrons and pions. This isn't like a chemical reaction or even a standard radioactive decay. It is a fundamental unraveling of the matter that makes up the universe. If the proton can decay, then the very concept of solid matter is merely a temporary phase in the life of the cosmos. Everything we see, stars, planets, and the memories stored in the structures of our brains, is built on a foundation that is slowly, invisibly, rotting away. The reason we haven't witnessed this yet is that the predicted lifespan of a proton is staggeringly long. Current experiments, such as the Super Kamiokande in Japan, have established a lower limit for the proton's half-life at roughly 1,034 years. To put that in perspective, the universe is only 1.38 times 10 to the power of 10 years old. If you were to wait for a single proton to decay, you would have to outlive the current age of the universe by a factor of trillions. Because the time frame is so immense, we must build massive detectors filled with thousands of tons of ultra-pure water, hoping to catch the telltale flash of light from just one single proton among decillions, finally giving up the ghost. If proton decay is real, the future of the universe is a slow descent into a photon age. Long after the last stars have burned out and the black holes have evaporated via Hawking radiation, the remaining iron stars, those cold, black spheres of stable matter, will begin to lose their mass. One by one, the atoms of these spheres will dissolve. The protons will vanish, leaving behind only light and subatomic wreckage. The universe will eventually reach a state where no two particles are close enough to interact. It will be a cosmos populated only by a thin, lonely fog of electrons, positrons, and photons, expanding forever into an absolute void. This uncertainty forces us to reconsider our place in time. We view the laws of physics as static, but they may actually be a slow-moving script for a total erasure. If the proton is unstable, then the material era we live in, the time of things and objects, is just a brief flicker in an eternity of radiation. We are the temporary inhabitants of a structure that was never designed to last. Our DNA, the code of life, is written in an alphabet that the universe will eventually stop recognizing. The search for proton decay is, in many ways, the search for the universe's ultimate end state. If we find it, we confirm that matter is an anomaly, a temporary condensation of energy that will eventually return to the light from which it came. If we never find it, it may simply mean that the proton's life is so long that the universe will end in some other way before the first atom in your body has the chance to dissolve. We are existing in the tension between an eternal foundation and a slow-motion evaporation, waiting to see if the building blocks of reality are as solid as they feel. The singular origin. The fact that the entire observable universe was once compressed into a point smaller than an atom suggests that our reality emerged from a state where the laws of physics as we know them ceased to function. This is the conclusion of general relativity when we wind the clock of cosmic expansion backward. If the universe is growing today, it must have been smaller yesterday. Follow that logic to its ultimate end, roughly 13.8 billion years ago, and you reach a singularity. This isn't just a very small, dense ball of matter sitting in a dark room. It is the point where space and time themselves began. Before this moment, where and when simply did not exist. At this singular point, the density was infinite, and the temperature was beyond any scale we can measure. In such an environment, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were likely fused into a single unified superforce. Our current understanding of physics is based on the separation of these forces. We have one set of rules for the very large, general relativity, and another for the very small, quantum mechanics. At the moment of the singularity, these two frameworks are forced to occupy the same space, and they immediately break each other. The math produces infinities, which is the universe's way of telling us that our equations no longer apply. The scale of this compression is truly mind-bending. Every star in every galaxy, the billions of light-years of void, and the very atoms that make up your body were all once squeezed into a space smaller than a single proton. This implies that the emptiness of the universe is a secondary development. The original state of reality was one of total, absolute density. Everything was once one. This historical unity is the reason why the universe looks so similar in every direction. It all started as a single, synchronized point of data before the period of cosmic inflation blew it up to astronomical proportions. However, the singularity creates a causal boundary. Because the laws of physics break down at the moment of origin, we cannot use science to look behind the curtain. We can trace the history of the universe back to a fraction of a second after the Big Bang, but the origin point itself remains a mathematical blind spot. We are like detectives arriving at a crime scene where the laws of logic have been scrubbed from the walls. We see the smoke and the debris, but the spark that caused the explosion is hidden behind a wall of infinite energy that our current theories cannot penetrate. This realization suggests that our reality is an emergent property. The rules we live by, the fact that light travels at a certain speed or that gravity pulls objects together, are not necessarily eternal or fundamental. They are the frozen remnants of a chaotic beginning. If the initial conditions of the singularity had been slightly different, the resulting universe could have had 10 dimensions instead of 4, or gravity could have been a repulsive force. We are living in the aftermath of a breakdown, governed by the laws that happened to settle out of the cooling debris of the Big Bang. We are left with the unsettling thought that our entire existence is a phase transition. Just as ice crystals form patterns when water freezes, the structure of our universe, the galaxies, the stars, and the laws of chemistry is just a pattern that formed when the infinite heat of the singularity began to cool. We are a complexity that grew out of a state of perfect, simple nothingness. The singularity is the ultimate measurement, a 0 point that reminds us that everything we consider solid and permanent was once nothing more than a mathematical point of infinite potential, waiting for the rules to begin. The infinite regress of multiverses. If the universe is truly infinite, then every possible arrangement of matter must occur somewhere, meaning there are infinite versions of you living out every possible life you can imagine. This is not a flight of science fiction, but a mathematical consequence of a flat and infinite cosmos. In a universe with no end, the laws of probability dictate that even the most unlikely configurations of atoms, the specific sequence that makes up your brain, your memories, and the room you are sitting in, must repeat. Not just once, but an infinite number of times. We are forced to confront the idea that we are not unique individuals, but merely one iteration of a cosmic template that is being copy-pasted across an endless sea of space. This concept arises from the cosmological principle, which suggests that on a large enough scale, the universe is uniform. If you travel far enough in any direction, you will eventually run out of new things to see. Because there are only a finite number of ways to arrange particles in a given volume of space before they must repeat, an infinite universe becomes a hall of mirrors. At a distance of roughly 110,280 meters, there is likely a volume of space that is an exact duplicate of our own. In that volume, another you is reading these exact words, having made every single choice you have ever made, down to the last blink of an eye. But the regress goes deeper than simple repetition. If we look toward the theories of eternal inflation, our entire Big Bang was just a localized event, a single bubble forming in a vast, ever-expanding multiverse sea. In this scenario, the vacuum of space is constantly churning, spawning new bubble universes with different physical constants. In some, gravity is too weak to form stars. In others, the laws of electromagnetism prevent atoms from ever bonding. This creates a landscape of infinite variety, where every law of physics is tested. We are merely residents of a lucky bubble, where the conditions were tuned for complexity. The problem with an infinite regress is the loss of self. If there are infinite versions of you, which one is the real one? In one universe, you took the job you turned down. In another, you never met your partner. In another, you are currently the ruler of a global empire. This suggests that your identity is not a singular, precious spark, but a statistical distribution. Every choice you make doesn't just change your life. It merely selects which version of the multiverse you are currently experiencing. The now becomes a thin slice of an infinite loaf of bread, where every other slice is just as real as the one you are holding. This leads to the Boltzmann brain paradox, a disturbing measurement of probability. In an infinite fluctuating universe, it is statistically more likely for a single, disembodied brain to spontaneously fluctuate into existence out of the vacuum, complete with false memories of a life and a world, than it is for an entire, complex universe to evolve over billions of years. If we take the infinite regress to its logical conclusion, you have no way of proving that you are a biological entity on a planet called Earth. You could simply be a temporary fluctuation in the void, a ghost brain that will vanish back into the vacuum in the next microsecond. The infinite regress of multiverses strips away our sense of narrative. We like to believe our history is a unique path through time, but infinity suggests that all paths are being taken simultaneously. We are, standing at the center of an explosion of possibilities that never ends. The measurement of our world is not an observation of a finished product, but a glimpse at one tiny, repeating pattern in a fractal that goes on forever. We are forced to accept that the edge of our world is not a physical wall, but a threshold beyond which our uniqueness dissolves into the inevitable repetition of the infinite.